everyone. Excuse me. So I just finished correcting exam number 4, and I post the grades. You by now you might know the grades, and I thought would be good to go over concepts of energy. I know that specifically what we did in exam 4 is not going to be in exam 5. Exam 5, I have pretty much conservation of momentum, um, rotational situations, and pretty much that is exam number 5. But um, exam 4 is the core of our course, along with Newton's law. So 3 and 4. So the laws of motion we explore in exam 1 and 2 is just to help out in what we are doing now. So when I saw several grades low, I that raised a red flag. So um, considering that, perhaps during the weekend we all might find time to do some extra work, and perhaps I will be available if you need anything to email me, and I will be happy to help you out. Um, but I decided to go over the solutions of the exam number 4 and put in a video and send to you. You don't have your exam, so but you see the questions as we go. First of all, before I start, is I would like to remind you of two things. When we do Newton's law, oops, wait a second. When we do Newton's law, we need to deal with forces. So Newton's law is forces. And forces is that little thing that has an arrow and is associated with acceleration, right? Because um, if you have a system with several forces acting on it, so you have a tug of war with several actions going on, and let's suppose you have some resultant. So you have a bunch of kids pulling this direction, another kids pulling that direction, you have another one pulling that direction, so on, so on, so on. So when you add all these different forces, there is what we call a resultant force, and this resultant force is equal to ma, which means if the body has a given mass, um, that force will provide the body an acceleration in meters per square second. Okay, very good. This is one thing. The other thing is force that is acting on a body and move that body over a certain distance produce what we call work. And the magnitude of the work done by a force is equal to FD cosine theta, theta being the angle of these two vectors. But work is associated with the concept of energy. This is another thing we studied. So energy is not force. Energy is not force. Energy is a different quantity in physics, and it's important even to define uh, quantities such as power. I mean, we talk about power. What power is the energy a system has and is consuming or producing or losing per unit or losing per unit of time. Power is energy per time. So see how these concepts play along? When you pay energy in your PG&E bill, you are paying the amount of uh, joules per hour, and we call that watts. So we are um, paying the amount of energy um, per second, and the PG&E charge us for that. Okay, so it's a different concept. I just would like to remind you that because I thought as students who got low grade, they still have not clear what forces are, what energy is, what velocity is, what spring constant is all kind of a big mumbo jumbo. And it's time to get those concepts straight. So the first problem is you have a bunch of enunciate, but basically we want to find free body diagram of these two blocks. Free body diagram is indicated by vectors. Here you have the gravity or the weight, mg, another force that is pulling up tension, and if this pulley rotates in that direction, there is a tension force, there is a weight of this block, right? A weight of this block, B, and there is also a normal force. Now, if in addition to that there is friction, and if the direction of motion is this, direction of motion, then this is your friction force, and the friction is kinetic. Okay. Now, problem number 2 is a classical energy. Right? So, I don't know why I did that. So there is a slope. You have a child that slides down a snow-covered slope on a sled. Top of the hill, her mother gives her a push with a speed of 1.5 meters per second. And there is a frictional force that is said to be 1/5 of the combined weight of the child. So 1/5 of combined weight of the child, and the weight is mg, 1/5 of mg there is. So it is true that kinetic friction is equal to coefficient of kinetic friction times normal, but we do not have in this problem neither the coefficient of kinetic friction or the normal, because we don't have the weight in newtons of systems led child. Okay. And they kind of slide down 29.8 meters, right? So this distance is pretty much 29.8 meters, and they get to the bottom with a final speed of 4.7 meters per second. So calculate the angle the hill makes with the horizontal, blah, blah, blah. Okay, very good. So there are several approaches to this problem. And some students, they saw this initial velocity, the final velocity, and the displacement, and immediately they thought about Bernoulli equation and got the acceleration, right? And that's a good approach. You could use also conservation of energy, since we are dealing with conservation of energy. We could use the concept of work kinetic energy theorem. So I'm going to use the work kinetic energy theorem. Total work of all forces. So work of all forces on the sled is equal to the change in kinetic energy of that system. And change in kinetic energy is half m v final square minus v initial square. So it's true we don't have the mass, right? So, but let's see if we can get at least to the end of it. So the right-hand side of the work kinetic energy theorem is solved. So how do we resolve the left-hand side? So we have to find the work of all forces on the sled, which means we need to find out what the forces are. So we have the work of gravity, we have the work of possible normal force, and we have the work that the frictional force, kinetic frictional force, do. Now, the work of normal is 0. Why? Perpendicular to the displacement. The work of gravity is given by mgh, mg vertical displacement. And in one of the problems, several students forget that. And then you have a negative work done by the friction. So what is the work of all forces? Is the work done by gravity, and that is mg vertical displacement, which is 29.8 sine of the angle theta, time mg sine angle theta time displacement. So either you can see this as mg vertical displacement, or you can see that mg sine of theta, which is the projected force of gravity along the x direction, is the component that is really doing work along the x direction. So if you take this component mg sine theta and multiply it by displacement, you have the work done by gravity. And the work done by friction is a negative work given by the friction times displacement. But the friction is given, is half of mg, right? It's half of the weight, and we have a negative there. So when you add those two, what we got is mg that multiplied 29.8 sine of theta minus times 29.8 minus 29.8 fifth. That is the total work. So the total work is right here. So what we want to do next is, well, the total work, mg times 29.8 that multiplies sine theta minus 1/5 is equal to the change in kinetic energy, half m v final square minus v initial square, and mass goes away, and then we can find our angle, right? There is only, I mean, we know everything. We know this, we know that, and then we divide all of that by 29.8, and then we can find our angle, okay? So this problem, we have a 2 kilograms block that is placed at the top of this track, and the track is sufficiently long. The radius is 3 meters, so this distance here is 3 meters. The coefficient of kinetic friction is given, and the block is released with an initial speed. Right? So you have an initial speed, and where does the block stop? So the block stop, let's say, at somewhere here, right? So you can use conservation of energy again to do this problem. To use Newton's law is complicated, and I have one student who, when that student do the free body diagram here, it put it normal force, and there was a friction force, and then it puts some curved vector. Curved vectors can't be curved; it has to be pretty much straight. Anyway, so this is not, that's not good. Yeah, take that out. There you go. So we can, I mean, Newton's law is complicated. Is really complicated. The force of friction is well, in fact, there is no friction, right? The quarter cycles are frictionless, but not on this rough surface right here. So, but it's complicated. So, a nice way of doing is you use conservation of energy. How do you do that? Well, when you do conservation of energy, we mark one particular spot, we mark the other spot, and we compare, we do the budget, we do the accounting of energy. So how much energy I have there, and how much energy I lost as I went from that point to point B, and that is the energy I have left at point B. Okay, and you have to go through the list of energy we studied. We studied kinetic energy. We studied potential energy, gravitational one, right? mg, vertical displacement. We studied potential energy of a spring, half kx squared, And we also mentioned that sometimes we have to include the work as an energy, the work done by external forces. We have to include that too. So let's see what we got. So we do a little table, and we call the energy at point A, point B. We list the energy. So at point A, let's see, is there any kinetic energy? We do. Half mass of the block times its speed squared. So we do have energy at point A. Point B we don't, because the block stops. The velocity is 0. So we would write half m0 squared, which is 0. Now, do we have gravitational potential energy? Yes, we do. So block B is at a certain height from the floor, which is 3 meters. And what is the value of a PG? PG is mg vertical displacement. So it doesn't care if you go from here, right, from here to there. You care for vertical displacement at that point. So let's write this down. It's mg times vertical displacement, and that distance is 3. At point B is my baseline. So my baseline I'm calling 0. That's it. So what else do I have? I have this, I have that, I have the work done by other forces. What is the work done by other forces? Negative of the coefficient, the frictional force times displacement. So that's it. So once I add these quantities, and I'm going to have 0 in cell B, there's no energy in there, I'm left with half times 2 times 1.5 squared plus 2 times 9.8 times 3 minus. What is the friction force? The friction force that happens to exist in this segment here. This is the only part with friction. So we don't have friction here. We don't have friction there. But we do have friction here. So it is given by the friction force's coefficient of kinetic friction. Let me take this 0 out. Coefficient of kinetic friction times the normal force. But the normal force when the block is down here, the normal force is equal its weight, and the weight is mg, times the displacement d equals 0. So we have one equation with one unknown, which is d, right? And then we can solve. Repeat the problem, assume there is no friction involved. Well, if there is no friction involved, what's going to happen? So if there is no friction involved, you get to this point with an initial velocity of initial speed of 1.5 meters per second, no speed, and it's going to go up to the same height with the same speed. The difference is the velocity now has a different component. So this block is going to go all the way up and stop momentarily at this position. So what I want you to calculate is this height, right? This height h is given. You could use Bernoulli for that, right? So final velocity square is equal initial velocity square minus 2 times g times del y, and then you find what is your del y right there. Could use that. Some students, they weren't fun. They say, well, it gets to that point, and then it reverses back, falls in the same position, and keep just going up, and so on, so on, so on. In fact, it reminds me of. Can I show that? I think I can. Let me show you this. So you take this cool dude over here. There is no friction, right? It's kind of the same idea. You could build segments, but See, the wheel is right there. So no friction, it's going to go to the same spot right there. Okay. And this does not depend on mass. Really don't. Mass small, bigger, it's always the same. Really doesn't matter. So let me do a pause right there. Now what I would do, see if I can do an initial speed. It doesn't give me initial speed. I would like to put an initial speed here and see what happened. But doesn't give me. Just give the speed of the person. Okay, well, sorry. Yeah. Okay. Well, but it's cool. I hope you enjoy this. Okay. Going back to the problem, and now this is another problem. We have a mass m. So I know we are now dealing with rotation. You are not paying attention too much to this type of problem, but the problems with rotation solve the same way as this problem if we use conservation of energy. Part A, that's how we call part A, and we call the moment when the spring is all collapsed, part B, and the del X. Now you guys learned this a lot, right? So this is your del X for the spring. So let's read the problem. You have a block that has a mass of 14 kilograms. It's released from rest on a frictionless incline to make an angle of 25 degrees. And the spring constant is given. The block momentarily stops when you compress the spring by 5.6 centimeters. So this is, please, I still have students that do not convert centimeters to meters when do problems and get it wrong. And now I have to take points out. This is important. When you punch your information, you have to make sure you have your units correctly displayed. So 5.6 centimeters is not 5.6 meters. How far does the block move down the incline from its rest position to the stop point? So you have a compressional force. So what do we have at point A? So when you do your conservation of energy, that's what you need. A, B, you are going to describes the possible energy. Let's start with kinetic energy. Now, here's the problem. And please, several students are trapped when they don't know what the concepts are and they read equation sheet. In equation sheet, you have one of the equations like this: K is equal half mv squared. And you have another equation that was like this: F spring is equal K del X. Certainly, by now, we all should know this K is not the same as this K. This is kinetic energy. This is a spring constant. They are different. One is in joules, the other one is in newtons per meter. And I had the students that were calling kinetic energy at point B 13,000 because K was given 13,000 as a spring constant. In the following problem is even worse. This problem over here, several students got the spring constant used in the previous problem right here, right? This problem, you have to find the spring constants. They found the spring constant K is equal something. And now you want to measure velocity. They did K is equal half mv squared, except that K was the spring constant, right? So you have to know what you're applying. or you are in big trouble. Anyway, so energy, kinetic energy. Point A, you have none because the block's not moving. It doesn't come out with an initial velocity. Part B, you don't have kinetic energy because the block stops. Now, how about a spring? Does part A has any spring doing work? No. Part B you do. Half K times del X squared. This is the expression for potential energy of a spring. Half K del X squared. Okay. Now, what else we got? Do we have gravitational potential energy? Several students forgot that. Well, at point A, I do. And what is it? It is equal to m times g times vertical displacement. And vertical displacement, h, is pretty much the displacement along x-axis times sine of that angle, 25. Okay? And pretty much that's it. So we have the mass, it's right there. G, you all know, 9.8. Sine of 25, you should have in your calculator. So you make this quantity equal to that quantity and you solve for D. Number 5, a spring compressed del X, compression 13.5 centimeters. Again, several students got it wrong because they didn't convert to meters. It stores that much energy, work, or PE spring, or 1.76 joules. That's energy that was stored, which is equal to half K del X squared, and you can solve for K. So K is equal to times 1.76 divided by 0.135 squared. And this K is in newtons per meter. Okay. The part B, here's the situation. You have this spring compressed, you put a pellet in there, and then you release it. And then at this point, the pellet is detaching from the spring, and it has moved certain del Y. Okay? So the spring was compressed del Y, and when released that much energy. Now, I was not picky. I should take points, but I did not. Because it's not going to make a lot of difference, but the proper way of solving this problem is you have a part A and you have a configuration B. You do your energy conservation grid again, A and B. Which energy you have in A? Do we have kinetic in A? No. Do we have it in B? Yes. Half mvb squared. And by the way, I want to find the VB. That's what I want to find. Now, do we have gravitational potential energy making tricks? Yes. And all of you, I didn't have one student who got that right. All of you forgot that. So there is. So you have a up and down thing going on. So what do? You take PEG, set a part A to be 0. There you go. And at part B, you have potential energy as well, which is mg del Y. What else do we have? Well, do we have a spring? Yes, we do. In A, we have a spring, which is given by half K, the K we calculated in the previous step, times del X squared. So that entire compressed energy, which is right here, is used to move this pellet up to this position and to give it certain kinetic energy. So the problem is solved. So that half K del X squared. So we have this and we have this, right? We have both. Plus, no, this much is equal, sorry, is equal, this is equal to m, which we have, g, which we have, del y, which we have, which is del x. I'm calling del x, del x, del x, right there, del x, del x. So mg del x plus half mv squared, and then we can solve for v. Ignoring a resistance, what is the maximum height achieved by the pellet? So this the only thing I kind of gave it simple, right? So what do you do? M G H, the maximum height, is equal to the energy you have once the pellet was released, half mv squared, and then you can solve for that. Number 6, it's a homework problem. We have an object, mass given, released from the rest with this angle, and the only difference from the homework, I add friction. So again, energy conservation, point A, point B, and you have friction all over the way, right? So you do your table with energy conservations, A and B. So you could call this part here your ground level, but you could call any other position too. So let's start with kinetic energy. Does it have kinetic energy at part A, part B? No, it don't. Does it have gravitational potential energy? Yes. At point A, it does have, and that is mg8. So m is pretty much m is pretty much 5, g is 9.8, h is 12, I think. It's right there. And at point B, you have 2, right? And that's what one of the, you want to find that. Call this HB. So MGHB. And we want to find HB. Why? Because sine of theta 2, which is 25, is equal to HB divided by this length over here, D. And that's what we want to find, right? So we want to get D. Look at this. How far the second ramp is measured along the ramp. So we want to find D. So which means if we find HD, we can find D. So what else we have? Well, here's the problem. There is friction. So there is work done by order, which is friction, and that work was given negative 150 joules, right? That's it. You add this quantity cells, mg8 minus 150 is equal mg8 times hb, and then you can find hb. mg8 minus 150 divided by mg. Okay. And the extra credit was, what is the minimum coefficient of, okay, so the block gets to this point and you don't want the block to stop momentarily and fall back. You don't want that to happen. You wanna the block to stay there. So if the block stay there, what are the forces playing a game here? You have the weight of the block, you have the normal of the slope on the block, and if you don't add friction, this component of the block weight will bring the block down. So you want to have a static friction that is able to hold that in place. So the minimum possible coefficient of static friction will be the one that will allow for that force to happen. So essentially you want your static frictional force to be equal to the coefficient of static friction times the normal force. So you want this force to be equal, this force, to be equal to the projected gravity along this direction, and that is Wg sine of the slope, 25. So you want Fs to be equal to mg sine of 25. But what is normal? Well, normal is mg cosine of 25. So basically, your coefficient of static friction must be equal to tangent of 25.